So thank you. I'm very grateful to the organizers for offering me the opportunity to give this talk and to spend a period here in this nice scientific atmosphere. And the starting point of my talk is a very, very simple setting. So we start from a periodic Schrödinger operator in Rd, but don't worry, because in few slides a non-trivial and non-linear problem will appear, which will make the things more interesting. So we start with an operator in the form minus Laplacian plus V gamma, where V gamma is assumed to be periodic with respect to the lattice generated over the integers by a basis E1, Ed. And in front of this audience, there is no need to recall that gamma is the periodicity lattice, which shouldn't be confused with what the physicists call the lattice, so the position of the atomic cores. And for example, if you deal with graphene, so with an hexagonal structure, then you have these vertices, but what we are interested in is the lattice generated by these fundamental vectors. For example, these two or these other two, or any equivalent choice. Okay, we will make the usual Kato-type assumption on the potential. For example, in dimension 3, we ask that V gamma is locally L2. In order to assure that V gamma is infinitesimally small with respect to the Laplacian, and then defines a self-adjoint operator on the Sobolev space W22. And as usual, we want to exploit periodicity through Bloch-Floquet theory. And I personally use a variant of the Bloch-Floquet transform, which is the one given at least for Psi continuous with compass support by this formula. So with respect to the usual definition, I add a y here. And the reason to do that is that now, for every fixed k, the transformed wave function is exactly periodic in the position variable. And so it defines for every fixed k an element of this Hilbert space, HF, which is given by gamma periodic function over Rd, or if you prefer, functions over the torus. Okay, this space will be called the fiber Hilbert space and will be important in the following. So we have exact periodicity in y, but the price to pay is that in k we don't have exact periodicity, but if you move from k to k minus lambda, you get a y-dependent phase, which we reinterpret as a unitary operator acting on the y variable, so on the space HF. And now we want to extend this definition to a unitary operator from the full Hilbert space to some other Hilbert space, and in order to have surjectivity, it's convenient to introduce this space, h tau. It consists of functions from the momentum space to HF, which are locally L2 as vector valued functions. And more crucially, they satisfy this property, which encodes exactly what we have seen here. So this pseudo-periodicity in momentum. Okay, now there is quite a boring slide, just because the notation changes from speaker to speaker. Just to remind my notation, for me in position space I have a periodicity lattice gamma, and the corresponding torus will be denoted by this symbol, while in momentum space, in the dual space, we will have the reciprocal or dual lattice, which is given by the set of momenta, okay, such that k dot gamma is an integer multiple of 2 pi for every gamma, and a fundamental cell for this dual lattice gamma star will be denoted by B, to remind the Brillouin zone. Okay, and occasionally we will regard this Brillouin zone as a torus, but then a star will appear to distinguish from this other torus. Okay, okay, this was the boring slide, and let's continue with the Bloch-Floquet, with this modified Bloch-Floquet representation. So we all know that the advantage of this transform is that a periodic operator, as minus Laplacian plus V gamma, becomes, after conjugation with U, a direct integral. So it's decomposed into a family of fiber operators, which have a very explicit expression. And the advantage to use the modified Bloch-Floquet transform is that now they act all on the same k-independent domain, which is this one, in the fiber Hilbert space. Okay, is well known that every fiber operator has a compact resolvent, and then a pure point spectrum accumulated at infinity, and when we move k, we get the block bands, which are denoted by this symbol, and the eigenvector will be denoted by this symbol, okay, while the eigenprojector on the nth band by this symbol here. Can you see? Because from my position, I don't see. It's clear. Okay, probably have an angle too. Okay. Okay. Physicists call block function this quantity, so the u multiplied by a phase, which makes it exactly periodic in K. But with a little abuse of terminology, I will call u the block function. Okay, this is the periodic part of the block function. So the okay, so let's give this definition. So a block function corresponding to the nth block band is any element of h tau, so it's understood that it must be tau equivariant, pseudo-periodic in K, such that for almost every K is an eigenfunction of the Hamiltonian, and is normalized to 1. And a trivial remark, but with many consequences, is that this eigenfunction is not unique. If u is any of these eigenfunctions, then another one is given by u tilde, which is obtained by multiplying the previous one by a k-dependent phase. So we have a wide freedom to choose the eigenfunction, which is parameterized by functions from the torus to the unitary circle, to the unit circle, and this will be called block gauge. Now we are ready to give the main definition, the one of Wannier function. So choose a block function, un, and then the corresponding Wannier function is by definition the pre-image through the block-Floquet transform of the function un, okay, which after a short computation is given by this expression. Okay, notice that although it is done in the physics literature, it is misleading to talk about the Wannier function for the nth band because of this block gauge freedom that I mentioned. Okay, now there are some elementary properties of the Wannier functions which follow in few minutes from the definition. So first of all, if we translate in position space, we have the same expression with here this exponential character appearing. Second, if we normalize the eigenvectors, so the block function to 1 or to any constant which is k independent, then in view of the orthogonality of the trigonometric polynomials, one gets that the Wannier functions which are obtained by translations with a fixed index n are mutually orthogonal. Okay. Okay, under this condition, then we have that this family of Wannier functions, so fixed n and gamma varying over the lattice, is a complete orthonormal basis for the pre-image in position space of the range of Pn. And if you let vary both the indices, so n and gamma both vary, then you get a complete orthonormal basis of the full Hilbert space, L2 of RD. Okay, now before we proceed, there is a short message from our sponsors. So basically, let's say I would move to the physics side to answer a fundamental question. So why are Wannier functions important? Okay, my understanding, discussing with physicists and reading the literature, is that they are particularly popular in solid-state physics because they are a good compromise between a localization in position space and localization in energy. So a good compromise, which is, of course, must be compatible with the Heisenberg principle, but is probably one of the best compromise one can have. And then there are some additional reasons why they are so popular. For example, they provide a visual insight of the structure of chemical bonds in crystals. For example, if you browse Physical Review B, you will find dozens of these pictures. What is depicted here are the level set for a small positive number and a small negative number of a maximally localized Wannier function. I will explain later what does it mean maximally localized. And on the left panel you have silicon, on the right panel you have gallium arsenide, and here you can see let's say how the distribution of electrons in a sense changes when in view of the different electronegativity of the atoms. Okay, the crystallographic structure is the same, but then you have different atoms, and you can see what happens. Okay, this is just a way to visualize what are called the orbitals, okay, the crystal orbitals. Then there are two probably more conceptual reasons. One is that in computational physics, when people try to develop numerical methods which scales well with the size of the confining box, then the existence of exponentially localized Wannier function allows to have a method which whose cost increase only linearly with the confining box. And third, they are very much used in the theory of polarization and orbital magnetization in, let's say, solid-state physics. Now, the issue 2 and 3 heavily depends on the fact that the Wannier functions are exponentially localized. And then there are two natural questions for mathematical physics. So is this always the case? And second, is there any algorithm to obtain these well-localized Wannier functions? So I will try to answer these two questions. So let's start with the first. So there exist exponentially localized Wannier functions. So to which extent are the Wannier functions localized? Okay, first of all, you can shift the problem to the block function, because the block Floquet transform is a sort of discrete Fourier transform, and then it's clear that the localization in position space of the Wannier function would correspond to the smoothness in momentum space of the corresponding block function. And indeed, you can take any textbook in Fourier analysis and reprove all the analogous theorems for the block Floquet transform. In particular, the Wannier function decays faster than the inverse of any polynomial if and only if the block function is infinity smooth. And the Wannier function decays faster than an exponential if and only if the corresponding block function has an extension, an analytic extension to a strip around the, let's say, around RD, a strip in CD. Okay, so we can move to this side of the diagram and study the regularity of the block function. So the next question will be then to ask how smooth is the block function, but this crucially depends on the gauge, on the block gauge. So the well-posed question is this a second. So is it possible to choose the phase, the block gauge, for the eigenfunctions in such a way that the corresponding Wannier function is exponentially localized? Okay, apparently seems not a very difficult problem, especially for an isolated band. Why? Because okay, if the band is isolated, then you can always write the projector by the Ritz formula. But if the band is isolated, you can choose a locally constant contour, which means the same contour which is good for k naught is also good for all the k which are at a small distance from k naught. Okay, this is because the band is isolated from all the other bands. Okay, and then once you have this representation, it's clear that differentiating with p with respect to k corresponds to differentiating the resolvent, but this fiber Hamiltonian is an analytic family of type A under our assumptions, and then it's clear that you will get, you can differentiate infinitely many times. And so the projector is infinity smooth, and with a bit more of work, and using again the fact that the potential is cut small, you will get also that this projector is analytic with respect to k in this strip. Okay, now we know that the projector is a smooth function, and then it's easy to see that you can choose the block function locally smooth. But this is only the first half of the story, because what might happen is that there is topological obstruction. In the sense, when you go across the torus in every open set, in every small open set, you can choose a smooth block function, but then when you wind once around the torus, you will get something else. And so there is competition between the regularity, which is a local issue, and the periodicity, or let's say the tau equivariance of u, which is equivalent to the periodicity of psi. Okay, the picture is a bit misleading because this is a real vector bundle, but okay, you can imagine the same situation with a complex vector bundle. Every complex line you can think is the range of a projector, which depends smoothly or even analytically on k on a one-dimensional torus, but it's clear that we will never find a global smooth and periodic, a global smooth eigenfunction which is normalized to 1. Okay, this is the reason why it took the problem required a lot of years for its solution. It was originally proposed by Walter Kohn in 1959, who also solved it in dimension 1 and for an even potential. Then a few years later, de Clouseau removed this condition, and in a second paper of the same year also proved the case of higher dimension, but for a centrosymmetric potential. And the first general proof appeared in 1983 by Nenchu, and a few years later, Bernard Delfer and Johannes Jostrand, in one of their papers about the derivation of the Harper operator, they also have a simpler alternative proof. Okay, all these results crucially depend on the fact that the Hamiltonian is real, so commutes with the complex conjugation, which is something a physicist would rephrase by saying that the system is time reversal symmetric. And okay, we know, because there are explicit examples, that this result is not true even for a single band if we break the time reversal symmetry, and this is usually done by adding magnetic potential, adding magnetic fields. So you can imagine to add a periodic vector potential, like in this case, then the operator commutes with the ordinary translations, and then is decomposed by the ordinary block-Floquet transform. So you have the same situation I described until now. But you can also include the case of uniform magnetic field. Okay, then the potential is linear, and the operator does not commute with the ordinary translations anymore. But as was noticed by Zach in the 60s, you can use the magnetic translations and then decompose this operator by using the magnetic block-Floquet transform, provided there is a rationality condition which is satisfied. Okay, so the magnetic flux per unit cell should be a rational multiple of 2 pi. Okay, this slide was just to say that in these cases there are examples which show that in general this line bundle is non-trivial. Okay, but what happens is that usually in 3 dimensions there are no isolated block bands. For example, here there is a numerical simulation of the block bands of silicon, and you will see that there are many band crossings everywhere. And but what happens is that in insulators and semiconductors there is a gap which separates the occupied bands from the free ones. So it's natural in this context to regard sigma star of k, to look at sigma star of k, so the spectral interval which contains, for example, all the bands below the spectral gap, or if you prefer, any other family of band which is isolated from the rest of the spectrum. Okay, so now we have not just one band, but a family of bands. Why we do that? Because okay, if you exclude the case of dimension 1, which is somehow exceptional, in dimension 2 and 3, whenever there is a crossing of eigenvalues, then the eigenprojector is not smooth at that point. Okay, in particular the derivative is singular. And then, okay, if there is no smooth projector, there is not even hope to have a locally smooth block function. Then we have to change completely perspective, and following Blount and de Clouseau, we consider the relevant family of bands as a unity, and we consider as fundamental object the projector P star, which is the projector on all the spectral interval sigma star, which can also be written in this way, when here I'm using the Dirac notation to denote the projector on the nth band. Okay, now we relax the notion of block function. So what is a quasi-block function? A quasi-block function is an element of h tau, which at almost every k is an eigenfunction of the eigenprojector. In general, it's not an eigenfunction of the Hamiltonian, but of the eigenprojector. Okay, we will also assume in the following that the dimension of the rank of P star, which is constant in view of the gap condition, is finite, and that all these quasi-block functions are normalized. Okay, now the question, before giving the definition of the physicist, I find very useful an intermediate definition. So a block frame is a family of quasi-block functions such that at almost every point k, phi1 of k, phi m of k is an orthonormal basis in the range of P star of k. So for almost every k, we fix an orthonormal basis in the range. And then we go to the definition of the physicist, which is rephrased in this way. The composite Wannier functions corresponding to a block frame are defined exactly as before as the preimage from modified block-Fourier transform of these elements of the block frame. Now the block gauge is even more relevant as before, because if phi is a block frame, then we can obtain another block frame phi tilde by acting with a unitary matrix, which will change pointwise the frame, and so we have a UM gauge freedom. Okay, now the question is, as before, is there a choice of block gauge which provides Wannier functions which are exponentially localized? And okay, here it's written more explicitly to see that again that we have a requirement. We have a requirement of periodicity, which is a global issue, a requirement of analyticity, and this constraint that at every point they form an orthonormal frame in the range of P star of k. Okay, the answers to question B start with a proof by Georg and Enchu in 1991, which was using adiabatic methods, while dimension 2 and 3 required more heavier use of geometric methods. And there is this couple of papers. In the first, it's shown that the block bundle is trivial under the assumption of time-reversal symmetry, and in the second, there is the application to Wannier function. And recently, with Domenico Fiorenza and Domenico Monaco, who is sitting here in the audience, we obtain a better result. So while the result of 2007 was rather implicit and abstract, now we have an explicit construction of the block frame, and moreover we can construct a block frame which implies that the corresponding Wannier functions are real valued. Okay, so we have the existence of real valued exponentially localized Wannier functions. Okay, okay, maybe I have to be quick on this. Okay, as it's clear from the introduction, this is the problem is equivalent to the triviality of a vector bundle, which we call the block bundle, which encodes this competition between regularity, local regularity, and periodicity. Okay, the bundle is basically the one such that the fiber over k is the range of P of k, but since we wanted to use a modified block-Fourier transform to have easy life with the domains and analyticity, then we have to pay a price that P is not periodic, but pseudo-periodic, or we call this property tau covariant. And then Okay, then we have basically just to take the quotient. So in the we consider two pairs k phi and k prime phi equivalent if this relation is satisfied. And then the total space of the vector bundle is basically the set of equivalence classes such that phi is in the range of p of k, which does not depend on the representative because of this condition. And then, okay, one has to prove local triviality, which can be done with the Kato-Nagy formula. So whenever two projectors have a difference which is smaller than 1, there is a unitary which intertwines among them, and this is the basis to prove local triviality. And the Hilbert space HF induced on the vector bundle an Hermitian structure, so an inner product on the fibers. Okay, now we have defined the vector bundle, and why is trivial? Well, the first part of the argument is very easy. It follows easily from time reversal symmetry. So since the Hamiltonian in the original space commutes with complex conjugation, when we go to the block-Floquet representation, we get a relationship between the fiber Hamiltonian at k and the fiber Hamiltonian at minus k, which is inherited by the projectors. Okay, here C is the complex conjugation operator in the fiber Hilbert space, and obviously it's square to 1. Okay, but I wrote that because okay, later there will be a different case. Okay, now we wanted to compute the Chern class, the first Chern class of the vector bundle. Then we choose a curvature, for example, the curvature of the Berry connection, which is a two-form over the torus, whose coefficients are given by this expression. Okay, I wrote it in a way such that is already clear and that is gauge invariant, since this definition it involves only the projector. But okay, if you are familiar with the topic, you will find in the literature a more standard definition by using just a section. But okay, I wanted to have the gauge invariant one. And now, equipped with this curvature, you notice that omega at minus k is given by the same expression in which c and c to the minus 1 appear at these edges. But now they are antilinear operator, so cyclicity of the trace doesn't hold true. And what happens is that you get a minus here, okay, because they are antilinear. Okay, you get a minus here. One can easily check by developing the trace on a basis. And then the first Chern class is the two-form, which is up to a trivial factor, is essentially given by omega. And this, we see it vanishes for all dimensions, because in dimension 2, okay, you have to integrate this form just on the two-dimensional torus, and you get 0 because it is odd. And for example, in dimension 3, you have 3 fundamental 2 cycles, which are the one given, for example, by the set of momenta in which the jth component is 0, and if you integrate on it, you get again 0. So, okay, the first Chern class is 0, and if we are in dimension smaller or equal than 3, then the other classes are automatically 0, and then we have that the Chern theory is 0. But this is not the end of the story, because unfortunately there are some vector bundles. We have trivial Chern theory, but are not trivial as vector bundles. Okay, this is the bad news. The good news is that they usually appear in higher dimension. Okay, they exist also on the torus, but at least in 5 dimensions, at least the examples I know. So one has to do something here to go from the fact that the first Chern class is 0 to the triviality of the vector bundle, which in particular implies the existence of a continuous and periodic block frame. And okay, this is the difficult step, the technical step in the proof, which exploits the fact that the torus is a very simple manifold, so you take advantage of this. And then, this yields a continuous frame. Now we use the Steenrod approximation theorem to prove that there is a smooth and periodic block frame which is arbitrarily close to the continuous one. Okay, and then there is still another difficult step from smooth to analytic. This is not true in general, so there is nothing analogous to the Steenrod theorem in general. But the torus, or better to say, the complex extension of the torus is a Stein manifold, and then we can also go here. Okay, by this theorem by Stein. And then when we are here, by doing block-Floquet transform, we get exponentially localized Wannier functions.
What is the complex extension of the torus?
Yeah, the fact that, as I said, the projector is analytic in a complex strip in CD.
Okay, so
okay? Then you take the quotient with respect to the translation by the lattice, and you get a d-dimensional torus which is extended in the imaginary direction.
Just a little bit.
Just a little bit, yeah. So it's, maybe it was too early.
No.
So you take this set, and then you divide by the action of translations. And okay. Okay, now as I said with Domenico, we have a better result recently, which is also in a wider context. So we write it in a general context. So the assumptions are the following. You have a family of projectors parameterized by K in Rd, which satisfy this assumption. It is smooth. It is tau covariant, so behaves in this almost periodic way, where tau is a unitary representation of the lattice group. This would be ZD. And then it's time reverse asymmetric, which means that P of minus K is conjugated to P of K by an anti-unitary operator, which either squares to plus 1, as before, or to minus 1. Why minus 1? Because we want to include also the case of particles with spin, where the canonical time reversal operation squares to minus 1. Okay? Okay, and then we have to ask, since we are in an axiomatic framework, we have to ask a compatibility condition between the time reversal operator theta and the tau, okay, which is satisfied in all the examples we know. Okay, now we want to specify what does it mean that a block frame is time reversal symmetric. And in the even case, when theta squares to 1, this is rather obvious. You ask that phi of minus k is equal to theta of phi of k for every index in the frame. Okay, but now for theta that squares to minus 1, the situation is more complicated. Why? Because consider this bilinear form, which is obtained by theta phi inner product with psi. Okay, this is antisymmetric when theta squares to minus 1, which means that, and is non-degenerate because theta is anti-unitary. Then it defines a symplectic form, which first of all implies that m must be even. And second, you notice that if you have a relation like that, at the point k equals 0, you pretend phi to be equal to theta of phi, which is impossible in view of the antisymmetry of this form unless phi is 0, which is forbidden for a frame. Okay, then we cannot ask anything like that. What is the natural thing to ask? That the frame if you evaluate this bilinear form B on the frame, you get the canonical form, the canonical symplectic form, which then can be rewritten in a more explicit way by asking that phi of minus k is equal to theta of phi, but then there is a reshuffling of the indices, which is given by the right action of this matrix. Okay, and now what is the theorem? The theorem is the following. Under this assumption, if dimension is smaller or equal than 3, then a block frame which is smooth, periodic, anti-reversal symmetric exists under the following conditions. Okay, if theta squares to plus 1, always. Okay, so for spinless particle, we have exactly what I said, there is always a time reversal symmetric block frame. If theta squares to to -1, then in dimension 1 there is no problem. But in dimension 2 and 3, an obstruction appears, which is parameterized by a Z2 index in dimension 2 and by 4 Z2 indices in dimension 3. Okay, this seems a complication, but on the other side, this makes the theory richer in the sense that we have found a different characterization of what is called the Z2 invariant of time reversal symmetric topological insulators. Okay, a topic which is now very, very mainstream, and in particular, this would be in the classification of topological insulators by Altland and Wirbauer. This would be the class A2. Okay, there is a very important open problem in this setting. I mention it because I know there are many people who are experts of random Schrödinger operators. So the problem is to find a good definition of the Z2 index for disordered topological insulators. Okay, the definition we give as the obstruction to the existence of smooth periodic and time reversal symmetric frames is based on block-Floquet theory. Okay, so the challenging open problem is to define it in the case of disordered systems. Okay, this was the first part of my talk. Now I would talk about maximally localized Wannier functions. So what is the historical origin of this notion? Well, in the 90s, there were certain controversy about the existence or non-existence of exponentially localized Wannier functions in 3 dimensions. And moreover, with the progress of computational physics, people wanted not only to have an existence result, but to have an algorithm to find these well-localized Wannier functions. And then Marzari and Vanderbilt suggested to change the paradigm. So instead of insisting on exponential localization, they wrote down a localization functional and proposed to look for the minimizers of this function. Okay, of course one has to guess what is the good functional, but okay, at the end it's very easy. It's given by the variance of the position operator with respect to the position probability measure. And so for a single band normalized Wannier function is given by this expression. Okay, if I have instead a system of composite Wannier functions, then I take the same definition and I sum over the index A from 1 to n. Okay, of course, I mean, it seems that if you look at the problem like that, it seems that that you can minimize if W tends to a Dirac delta. I mean, you can have a minimizing sequence as W tends to a Dirac delta, but this is not possible because there is the constraint that W is a Wannier function, so that its block-Floquet transform must be a block function in this case and a block frame in this case. Okay, so inspired by Marzari and Vanderbilt, we give the following precise definition. A system of maximally localized composite Wannier functions is a minimizer of the Marzari-Vanderbilt localization functional in a suitable set, such that every function is in the domain of H and the domain of X, under the constraint that if you take the block-Floquet transform of the W, you get a block frame. Okay, now there are 2 warnings. The first one is that the name maximally localized Wannier function is a bit misleading, at least to me, because I mean, they are not the most localized among all the Wannier functions. According to the definition, they are just the minimizers of a functional which essentially contains the squared, the variance of the position operator. So there is no reason a priori why they should be exponentially localized. And the second is that this is a truly nonlinear problem because you cannot linearize around W equals 0 because this is not a Wannier function in view of the topological constraint. Okay, so if you give a look to the review by Marzari et al. In Reviews of Modern Physics, you will see that there is convincing numerical evidence that this minimizers are exponentially localized in the sense that there exists a beta such that this integral is finite. And then we have two natural problems for mathematical physics. So first, to prove that the minimizer exists, this is the easy part, and second, to prove that each minimizer is exponentially localized. Okay, our approach is first of all to shift everything to the block function. So we transform by block-Floquet transform using the fact that it's an isometry and intertwines the position operator with the derivative with respect to k. We get a functional f tilde, which whose argument is the block frame, which is given by this expression. And of course, you have also to recall that you have to transform the minimization space, which becomes this complicated thing, in which, however, the most important information is that this block frame should be W12 local. Okay. And now, now we do another step. So we know by the abstract result of 2007, and also now also by the explicit construction of last year, we know that there exists an analytic block frame. Then we keep this frame key fixed as a reference frame, and any other frame will be obtained by unitary rotation of the reference frame. Okay, so the new minimization variable will be u, and in view of the previous condition, this W12 local, in view of this previous condition, then the u is a W12 function from the d-dimensional torus to the unitary group. Okay, this is a truly periodic function. This was a truly periodic function because both sides here are tau equivariant and the tau cancels. Okay, so now now we expand the functional. So key is fixed, and we write the functional in terms of u. And we get this expression, where a, the terms a, so this term is fixed, and the term a is given by this expression, and here the expert would recognize up to a constant the coefficients of the Berry connection. Okay, now it seems very complicated, much more complicated than before, but actually it's a beautiful functional, because the leading order term, that is this, is just the Dirichlet energy for maps from the d-dimensional torus to the unitary group. So namely, it's the functional whose stationary points are the harmonic maps. And then, okay, I was very lucky that in my department there is a colleague and a friend of mine, Adriano Pesante, who is an expert of harmonic maps. And then when, in a sense, it was realized that this functional is very similar to the Dirichlet energy, together we worked on the problem to reach the result. Okay, let me summarize what is the translation. So the infimum of the original Marzari-Vanderbilt functional on a set of Wannier functions, okay, which are in the space W, is equal to the infimum of this tilde functional, in which key is fixed and u varies in W12 from the torus to the unitary group. Okay, so now we will play with this second representation. And by doing that, later I will give some details, we prove this theorem. So we have existence of the minimizers if for a single band in any dimension, and in dimension smaller or equal than 3 for any number of bands. So under this condition, there exist minimizers of the functional. While for the case of exponential localization, we have dimension-dependent assumptions. So we have the result either in dimension smaller or equal than 2 for any number of bands, or for a single band in any dimension. And in dimension 3, for technical reasons that I will explain, we are forced to assume that m, the number of bands, is smaller or equal than 3. Okay, and under these assumptions, we proved that for any minimizer there exists a beta such that W times beta is in L2 of RD. Okay, this is the exponential localization. Okay, now the theorem leaves open the space to two conjectures, so we'll say problem for the future. Okay, one is the fact that the parameter beta, which is appearing here, presumably does not depend on the minimizer. And more precisely, one expects that the same results hold true for any beta smaller than alpha, where alpha is the size of the analyticity strip in the complex plane. And of course, the second conjecture, which is left out from the theorem, is that the results hold true for any number of bands, even in dimension 3. Okay, now I have 15 minutes to give some ideas of the proof. So let me first give an overview. So the existence of the minimizers is easy. It follows from the direct method of calculus of variations, with the only adaptation that one has to deal with the fact that the functional has a symmetry due to translations by the lattice gamma. No? So if W is a minimizer, W translated by gamma is also a minimizer. But this is the easy part. Well, for the analyticity of the minimizers in the sense of the functional tilde, okay, we use ideas and methods from the theory of harmonic maps. And in particular, as for the harmonic maps, the crucial step is to prove that a minimizer is continuous, because then there is a sort of well-established machinery to prove smoothness and analyticity. Then the proof that the minimizer is continuous is dimension dependent. In dimension 2, it follows from the particular structure of the Euler-Lagrange equation, and it holds true for any stationary point, not only the minimizers. While in dimension 3 is a special property of the minimizers, and it follows from the fact that the minimizers at smaller and smaller scale look like a minimizing harmonic map. And let's say something I will say about a Liouville theorem for harmonic maps. Okay, this was just an overview. Let's just enter in some details. So first of all, the Euler-Lagrange equation. So we take a free variation, so where u is in the minimization space, and phi is any smooth function, matrix valued smooth function. But then we have to project it on the unitary group. So we exploit the fact that there exists a well-defined nearest point projection map, and then we get the projected variation, which is given by this expression, okay, up to orders which are small o of epsilon. And then by using this family of variations, one sees that a stationary point of the functional satisfies these Euler-Lagrange equations. Okay, basically these have a special structure, so we can recast them in this way. The Laplacian of u is equal to this term, which is crucial, plus the sum or the combination of all the other terms, which yields something which is in L2, which will be not crucial. And now our problem is to prove that if u is in W12 and is a solution of this equation with f in L2, then u is continuous. Okay, and this is due to the special structure of this term, which can be recasted to use this crucial lemma, which is adapted from this paper. So basically, suppose to have an equation like that, in which you have a gradient, and B, which has all the components in L2, and is divergence free. Then U is W21. Okay, but then if it's W21, it means that the gradient is in the Lorentz space L21, and then by this you get, by the improved Sobolev embedding, you get that U is continuous. Okay, so in dimension 2, this is the proof that that the minimizers are continuous, then the usual machinery proves that the minimizers are analytic, and so the proof is concluded. In dimension 3, there is more work to do, so I leave these slides here for the expert, and I try to explain the results in simple words. So we want to prove continuity around a point, k naught. So we take a small neighborhood which is rescaled to be Rd minus, we are in R3, so R3 minus 0. Okay, and is rescaled by defining this map which is called U R k naught, which is k, which is the old U of k naught plus Rk. Okay, then we have a monotonicity formula which allows to conclude that as R goes to 0, this rescaled map up to some sequences converge to something weakly. Okay. But then the point 2, so some form of compactness of this set, allows to say that that this convergence is also strong. Okay, and now we have to prove that the limit U star, this is the neck of the bottle, we have to prove that the limit U star is constant. And why do we expect that? Okay, maybe I will, okay, we have to prove that, just I will comment in a minute, and then there is still a fourth ingredient which allows to conclude continuity. What is important is, why do we expect that this U star is constant? Well, because U star is obtained as a scaling limit of this UR, and when you do the scaling, all the subdominant terms in the functional disappear, and only the Dirichlet energy stays. So one can prove that this U star is a minimizing harmonic map of degree zero homogeneous. And then the conclusion is that if one is able to prove a Liouville theorem for such kind of maps, then this U star will be constant. So the neck of the bottle is exactly here. Okay, so this is what we want to prove, and here is the point where we have to assume that m is smaller or equal than 3. So first of all, okay, we obtain this U star, which is a minimizing harmonic map, is degree zero homogeneous. Then we can rewrite it in this form, where omega is smooth from the two-dimensional torus to un. Okay, the fact that it's smooth follows from the fact that is minimizing, that U star is minimizing harmonic. Okay, then the problem is which omega provides an harmonic map U star? Or in other words, we want to prove that if omega is not constant, then U star is not stable, so is not minimizing. Okay, for m equal 2, this was already known because SU2, first of all, we for our particular functional, we can reduce always to the case of the special unitary group, okay, up to multiplication by a constant matrix. And then for m equal 2, the result was already in the paper by Schoen and Uhlenbeck, because SU2 is isometrically isomorphic to the three-dimensional sphere of radius square root of 2, and then let's say we can take the result about the sphere valued harmonic maps. And for m equal 3, we use other ingredients. So one is done by us, and the other two are from the literature. So we prove this lemma. Okay, this is we call it a stability inequality. Take a test function in R3 minus 0, and then the gradient U star norm squared, weighted with the test function, is controlled by this gradient square of the test function integrated times a constant which depends on the basically on the dimension of the Lie algebra of SUM. Okay. Okay, now we optimize on the test function. Okay, there is a little bit of work to do here, which I am skipping. And then we get that if U star is stable, then the energy of omega, okay, is smaller or equal than this constant. Okay, now we wanted to use another important ingredient, which is the quantization of the energy of harmonic maps on the sphere, theorem by Valli, which tell us that this energy is an integer multiple of 8 pi, and in particular that the energy is 0 if and only if omega is constant. Okay, then for m equal 2, our inequality was already sufficient to conclude. Okay, and for m equal 3, we needed a more careful analysis. Basically, the last ingredient to use is this theorem by Uhlenbeck about the factorization of harmonic maps into unitons. What does it mean? Okay, it means that first of all there are some special unitaries which are given by the reflections with respect to the range of pi. Okay, this is the Poincaré embedding of the projectors into the unitaries. So for every projector, you take the reflection with respect to this projector, and this is a unitary. Okay, and then Uhlenbeck is saying the following: there exists a fixed unitary matrix omega naught, some constant, and holomorphic maps from the two-sphere to the Grassmannian of increasing rank, such that an harmonic map is factorized in this way. Okay, so first I have a constant, then a unitary which is reflection with respect to a small space, then reflection with respect to a larger space, and so on. Okay. Okay, here you see also that the rank are increasing. Okay, and then what is the point? The point is the following, that if m is equal 3, then we know by our instability inequality that the energy is smaller or equal than 12 pi, which means that either omega is constant or the energy is 8 pi. But okay, if you enter in the details of this theorem, you see that each factor, let's say this way, if the energy is 8 pi, then only one of these factors, which are called unitons, can be there. Okay, but then it means that we have just one of these, and this is a big simplification. Now here I don't want to enter into details. Here there are some dots to say that with this simplification, so to have just one factor instead of an arbitrary number, then we are able to go back to the previous case, and then the proof is concluded. Okay, this is all, and thank you for your attention.
Any questions?
Can you comment again how you got this Marzari-Vanderbilt functional? Where does it come from?
Okay, it comes from the paper by Marzari and Vanderbilt 97. And, okay, but this was not the question. No, basically, okay, how do they guess that this was a good functional?
What does it look like? What is minimized? Because when you showed the functional, it looked something very bad. Yeah.
Well, for every W, you have a number, no? For every W in L2 over Rd, you have a number which is finite whenever this quantity is finite. And then you minimize, but not in all L2 over Rd, but only in the set of Wannier functions, so with a special constraint that the block Floquet transform of W is a block function of unit norm.
So you minimize variation. The second moment and the first moment is there as well.
Variation.
The first moment so this is already the variation, no? The second moment minus the square of the first moment. Yeah.
Okay.
Okay. Any other questions?
The variance.
Just a remark that when we do, for example, semi-classical analysis, we sometimes take a converse point of view. That is, we start by constructing localized Wannier function for the eigenspace, and then we look at the restriction of the operator to the space generated by the Wannier function.
To obtain, for example, a tight binding effective Hamiltonian.
Then this problem of triviality of the bundle that you have with the 5xk, we get it later, because by analyzing the operator in more detail, we have to come back to this. So, because if you are just wanted to look at the spectral question, it's not necessary to impose that your Wannier function are obtained by this law.
Yeah, but then you use another definition of any function.
Yes,
Let's say
I changed
some complete orthonormal system which has some property.
Typically, if you have a semi-classical problem with wells, then you start to construct localized function near each well. The wells are on a lattice.
This is what I call the generalized Wannier function. So it's a complete orthonormal system which behaves well with respect
for
to
the spectral
translation.
questions, this could be another point of view, where the constraint of triviality will appear later in some sense. Because of course, at the end, you will find your bands on the staff.
Any other questions?
So in dimension 3, could you please remind what was the condition of the potential?
And it is locally L2.
Is it possible to improve it to 3 halves by using quadratic forms instead of operators? So
Yeah, I think, I mean, okay, the fact is that then you obtain an, okay, no, I think so, because, I mean, we need this condition essentially in 2 points. So first, to have a self-adjoint operator, and then would be fine also to use quadratic forms. And then we use it because we need that the fiber Hamiltonian is an analytic family of type A. And this is very easy if the gamma is cut small as an operator. Now probably, okay, you can use type A for the quadratic forms. Yeah, I think it's doable.
type B or something like that.
Yeah.
Okay, any other questions? Well, let's thank the speaker again then.